Today I'll be talking about using Kafka Streams as a data store for a workflow engine. And I'm the founder of LittleHorse Enterprises, which is a workflow company. And our workflow engine, big surprise, is built mostly on top of Kafka Streams. And by mostly, I mean it's the only data store that we actually have. And that was a pretty crazy design decision. A lot of people thought I was crazy when I did it, and a lot of people still think we are crazy for doing that. But today I want to explain why we did it, and in the process, we want to really understand Kafka Streams. And to me, Kafka Streams is a framework and a platform for building distributed data applications. And when you start to see that, you kind of will realize that there's a lot more you can do with Kafka Streams that you might not have imagined before. And in order to do that, we're going to first kind of learn how data is processed in Kafka Streams, how it's stored, how it's read. And if that all goes well, you might get curious and decide to check out Kafka Streams, play with their quick starts, and maybe even take a look at the LittleHorse workflow engine code, which is open source, and see a pretty interesting use case, or at least what I think is a pretty interesting use case for Kafka Streams. So we're going to start by going through Kafka Streams basics. This appears to have been the Kafka Streams room in the current conference. So if you've been here all day, you've probably heard a lot of these concepts before, but some people might be watching on the recording. Then we're going to go over the design goals. What is a workflow engine? How do our customers want to use it? And what does our system need to be capable of doing? And that will inform why we use Kafka Streams and how we can accept writes in LittleHorse, how we store that data, how we read that data, and how Kafka Streams provides fault tolerance and high availability. So without further ado, let's get going on Kafka Streams. Kafka Streams is a library. It is not just a library, but rather it is the library, which is actually probably the only library which allows you to embed stream processing into your Java applications. So in contrast to Apache Flink, Kafka Streams is not a cluster. It's not infrastructure that sits there that is managed by a platform team that runs with Apache Zookeeper and you submit jobs to. You do not submit a Kafka Streams job. Kafka Streams is a library that is embedded into your own application. And what it does is it allows you to build stream processing applications, process data in, data out, where the input and output to a Kafka Streams application is just data in a Kafka topic. So when would you use Kafka Streams? Generally, stream processing is broken down into two types of use cases. The first type is stateless processing, where you're maybe filtering out malformed records or filtering out data based on like the state or the country that the record represents, or perhaps message transformations, like blanking out PII fields. The more interesting one, which is what we're going to focus the entire talk today, is stateful processing. And in stateless processing, the inputs and outputs do not depend on what comes before or after. In stateful processing, the input and output of the application, your processing topology, depends on what comes before and what comes after every single message. So that means things like, if you're building a word count application, is the classic example of stateful application. So if in stream processing, a word count application would take in a stream of words as the input, and the output would be a stream of key value pairs where the key is the word and the value is the most recently seen count of how many times you've seen that word. So obviously, you can't just look at only one message at a time. You have to somehow persist state, which is how many times you have seen each word. Now, word count is not really useful. But some useful cases are, aggregation over windows, like perhaps sending an alert if you have seen 10 failed login attempts within, 100 milliseconds. That's probably an attacker. Something like joining streams. So if you have a stream of updates to the price of certain products and you have a stream of orders, joining them together, you can transform that into some more useful information about revenue. And lastly, materializing a view, which is taking a lot of information and transforming it, and there's views in SQL. You can also do views in streams. If you watched any of the TableFlow talks, you'll understand how that works. So we're going to revisit the diagram we saw a little bit ago, and it's now got a couple more components. As I said, Kafka Streams is not infrastructure. It's a library that you embed in your own applications. You deploy your own Kafka Streams applications however you want, using your own DevOps pipeline or whatever. And that means that somehow Kafka Streams needs to answer, well, where do we store this state? And the answer for that is it uses an embedded key value store called RocksDB. Configuring RocksDB is a bit of a beast. I did a YouTube talk on it a long time ago. But RocksDB is a C++ library that you can put into any application that allows you to put, get, and do range scans, basically, on keys and values, which are just byte strings. And there's a JNI wrapper, which is what Kafka Streams uses. And there's also internal Kafka topics, which, can you see my, oh, you can see this. This is amazing. There's also internal Kafka topics, which are used for repartitioning data and grouping them by certain fields, and also for providing persistence to the state. Because when you have stateful applications, one of the big challenges is, well, what happens when one server crashes? Where does the state go? How do you not lose it? How do you move state from one server to the other? And Kafka Streams has some internal ways of handling that. There have been bugs in the past, but a lot of them have been resolved, thankfully. So one thing about all of these use cases is, in the real world, they can be very high throughput. Like the login one, for example. There's some websites that have millions and millions of users. You can't process the stream of every login attempt on one laptop. So it's 2024, everything has to scale. In Kafka, the unit of scalability is the partition, the topic partition. So in a Kafka consumer group, you can have as many consumers actively processing data as you have as you have partitions in the Kafka topic that your consumer group is consuming from. Same thing with Kafka Streams, because Kafka Streams under the hood uses the consumer rebalance protocol. At least currently it does. Uses the consumer rebalance protocol to assign work to different instances. It will always have a consumer, but it's going to use the Streams rebalance protocol after the implementation of KIP 1071, which is going to move task assignment from the clients onto the broker side. Don't worry about that for the rest of this talk, because it will still be a consumer group, so everything we're talking about will still be mostly valid. So basically, you can scale Kafka Streams instances horizontally by adding, Kafka Streams applications horizontally by adding more instances. Let's zoom in on one instance and see what's going on. So here's a Kafka Streams instance, and there's 3 input partitions that have been assigned to this consumer in the consumer group. And within a Kafka Streams instance, there is a stream thread, or in this case, 2 stream threads. And a stream thread is what does the processing. It has a consumer, and it has a producer. The producer produces the output topic, the consumer reads records, and it does processing like filtering, mapping, joining, and stuff like that. We're not going to go into the DSL today because it's actually not used by LittleHorse. But this is, you can have parallelism within one Streams instance by adding stream threads. And a unit of work is a task, which is just basically corresponds to an input partition. If your processor is subscribed to multiple topics, then one task will have multiple input partitions. But in this case, and in LittleHorse's case as well, there's a one-to-one relationship between partitions, tasks, and also RocksDB stores. So some key points I want to make before we go further are that records are strongly ordered in Kafka within a partition. They're not necessarily ordered across partitions, but within a partition, you have strong ordering. And this allows for deterministic results in the case of replay, which is important for some Kafka Streams applications. Another thing to note, this is more of a performance thing, is that inside one partition, only one record is processed at one time. There is an asterisk there because there is a company called Responsive, which has built a managed Kafka Streams solution, which is absolutely fantastic. You guys should check it out for sure. And Responsive has in their platform the ability to process records in parallel asynchronously from the same partition in Kafka Streams, but still maintaining order based on key, which is very, very cool. And there's talks that someone might replicate that in the open source. We'll see. I have no visibility into that beyond what I've said so far. And another thing to mention that I want to really hammer home, and this is actually the real reason why LittleHorse uses Kafka Streams, is that state is stored locally in RocksDB. No network calls are needed to access the state. Now, this is kind of, in the era of cloud storage and Tableflow and Warp Stream, this is probably heretical to say, but it turns out this is actually a really, really good fit for LittleHorse. And we're going to talk about failures and rebalances and how that works a little bit later. I do also want to talk about exactly once semantics. And there's no such thing as exactly once delivery in distributed systems, but exactly once semantics are possible, which means that the result of the computation is the same as if the messages were all delivered exactly once. Kafka has transactions. Postgres has transactions. Kafka transactions and Postgres transactions are not the same. I am not a Postgres expert, so I won't talk about Postgres, but in Kafka, a transaction is basically the ability to write multiple records to multiple partitions such that all of the writes fail or succeed atomically. But how does this relate to Kafka Streams? So we want to achieve exactly one semantics in Kafka Streams. And LittleHorse needs this because we are a workflow engine, and we're working with some clients in the financial services sector on some POCs, and people would be very upset if they got charged twice. So very important to have exactly one semantics for us. Let's look at what it takes to process one record in Kafka Streams. So first, to process a record, you need to update the consumer offsets, which basically says, hey, I have processed this record. Another thing you need to do is update state. As we're going to see later on, the state in RocksDB is backed by a changelog topic. And that provides durability, fault tolerance, ability to scale. And the last thing you do is, in most Kafka Streams applications, funny enough, LittleHorse doesn't really do this very much, is you have to produce to the output topic. Because as I said before, Kafka Streams is a library that allows you to take data in and data out in Kafka. So the interesting thing about this is, since I think it was like Kafka 0.10, consumer offsets are no longer stored in Zookeeper directly, but rather as a Kafka topic. So all three of these things are actually writes to Kafka topics, which means they can be wrapped in a Kafka transaction, providing exactly one semantics. The real story of managing exactly one semantics in RocksDB is a little bit more complicated. There's a bunch of interesting KIPs about it. The most interesting one is KIP 892. Highly recommend you read it. I think I linked to it in the last slide. I think I should also mention the Kafka Streams DSL, and the first thing I'll say about it is LittleHorse does not use this, so I won't go into too much detail, but it's a bunch of high-level abstractions built on top of the core of Kafka Streams, which is the processor API, and to me, this is a cool thing that you can do with Kafka Streams, is the DSL, and LittleHorse is another cool thing you can do with the real meat of Kafka Streams. So, it allows you to do things like, map, filter, reduce, I got that backwards, join, and a bunch of other things like grouping by windows. And under the hood, the Kafka Streams DSL compiles to a bunch of processors. We only have 45 minutes, so we're not going to go over the entire DSL. So hold your horses. We're going to get to changelog topics and standby replicas and also interactive queries as we explain how LittleHorse works. But now let's talk about what is LittleHorse. And that's going to give you some of the design goals that motivated the decision to use Kafka Streams as the backing store for LittleHorse. So LittleHorse is a workflow engine, and basically that allows you to execute workflows reliably, where a workflow is a series of steps, and that comprises kind of a business process. And the reason this is interesting is building applications these days is getting a lot harder, because things used to be acceptable to do via 5 phone calls, now have to be done in a mobile app in like 10 seconds. Like 20 years ago, you expect to call Delta to book a flight. Now you should be able to do it in 30 seconds on a mobile app. So there's so many more APIs you have to integrate. There's so much more stuff that is expected of us as software engineers. So even if you're not working on Apache Kafka or Pulsar or like etcd or Kubernetes, you are a distributed systems developer just by virtue of building modern apps. And distributed systems are really, really hard. And that's the whole point of the workflow engine, is to make it easier, right? So the last thing about a workflow engine is you define a step of what should happen, and task workers are processes or programs that connect to the server and execute those steps. And the workflow engine tries to make it a little bit easier to make sure the whole process executes properly, so you're not worrying about dead letter queues, timeouts, retries, and the likes. So I'll go through like a 1-minute explanation of how a workflow engine actually works. So above the line, we have the brains of LittleHorse. Think of this as a thought bubble going, like what's going on inside this LittleHorse's brain. And here we have a LittleHorse server, and we have 2 task workers. So a task worker, as I said before, is just a program that executes a useful piece of business logic, and that code is written by the user of the workflow engine. And this workflow, basically what we do is it's a simplified version of the e-commerce checkout flow, where we charge a customer's credit card and then ship the item. So if I tell LittleHorse, hey, run this workflow, it'll create a workflow instance inside the LittleHorse data store. And we're going to talk through, not at the code level, we're going to talk through how that works at the Kafka Streams level. So LittleHorse will see, hey, there's this workflow instance now. What do we do next? Well, we go to the first node. That means we need to charge the credit card. So then LittleHorse, what it's going to do is it's going to dispatch a task to the payments worker. And it's going to say, hey, execute the charge credit card task. Payments worker is going to think about that for a little minute, and then it's going to say, hey, I'm done. LittleHorse server will get that response, think about what to do next, and then it'll decide, hey, let's move on to the next node in the workflow, which is the ship item node, and it updates the state of the workflow run. Then it will create a task and send that task to the shipping worker and say, hey, shipping worker, execute the ship item task. And then the shipping worker will think about it for a minute, probably make a call to the FedEx API, and then return, hey, I'm done. And then once again, LittleHorse will update the status of the workflow and move on to the next node, which says, hey, well, workflow's over. So why worry about workflows? As I said, distributed systems are hard. Networks can fail, servers can crash. You have to make your processes reliable. And people don't want to have their credit card get charged and then the product just not arrive at their front door. So you need a system that will ensure that these processes continue to complete in the case of failure. And also distributed tracing is really, really hard. There's a lot of people in this room today asking about, well, how do you trace stuff through Kafka topics and Kafka Streams topologies? Well, it's hard. Having a single point of coordination, understanding what's going on in your process makes that much easier. And then lastly, business processes are complex. And this part doesn't really have anything to do with Kafka Streams, so we'll not go into too much detail on that. So the requirements are we need to have reliable execution, which means we should avoid downtime as much as possible, and we should have some form of exactly one semantics. We should not lose data. We also need to be able to store and query workflow state. And it needs to be high throughput, which means we need to scale horizontally, and we need to have efficient use of network memory and CPU. Already we've seen how Kafka Streams provides horizontal scalability, and we're going to see how it allows us to store, query workflow state, and also how it gives us reliable execution pretty soon. So let's trace a write through LittleHorse. What happens when I tell LittleHorse, hey, run a workflow? And this is going to see how we use Kafka Streams, and then we're going to see why Kafka Streams was the right answer in order to achieve the performance that we want to achieve with LittleHorse. So we store a bunch of things in LittleHorse. We store the workflow specification, obviously, but more interesting, we store like workflow runs and task runs, and we're going to talk about that in like 10 seconds. And we also store a bunch of other things which aren't necessarily too interesting for now. So we're going to walk through the RPC run workflow, which is when we tell LittleHorse, hey, run this workflow. What data goes into Kafka? What data gets stored into RocksDB? What happens at the Kafka Streams level? And what network clients make what requests? So an interesting thing about this is that running a workflow requires a response. Because I say this is interesting because a lot of people think of Kafka as an asynchronous system. You write a record to Kafka, and you don't really get a response other than, okay, the broker has accepted this record, or it's replicated it to all of the in-sync replicas, and whoever processes it is kind of decoupled from the producer, and that is true, and that made this part of LittleHorse really, really hard. I spent a lot of late nights working on this. And why do you need a response for RPC run workflow? And there's other requests in LittleHorse where you don't need a response, but this one makes it more interesting. And the reason you need a response is because sometimes if a workflow already exists with that ID, you need to throw the already exists error to give some level of item potency. Also, you want to be able to validate the variables that were passed in by the user and provide some validation. So like, for example, we don't use HTTP codes because we're a gRPC application, but that would be returning, I think, a 409 or something. I don't know. And well, let's get into it. So as you might have guessed by now, LittleHorse is a Kafka Streams application. We have a Kafka Streams topology. It's a very simple topology, actually, but it does a lot. The green thing on yeah, you can see my pointer. The green box is our Kafka Streams processor. The yellow thing is a gRPC server. And this is a really interesting point about Kafka Streams, which Apache Flink can't do. Don't let Confluent hear me saying that, but you cannot put a gRPC or a Spring Boot or some other API on top of a Flink service. It just doesn't really work that way. But Kafka Streams is a library which you can embed into any application that you want, which allows you to do really, really cool things like this. So we also have this. We have a couple topics in our topology. The most important one is the command topic, which is where any update to any workflow lives. And all of these updates are partitioned by the workflow run ID so that every update for the same workflow ends up in the same place so that we can have a cohesive state of one workflow. So let's see what happens when the client says, let's run this workflow. I want to run a workflow, and the workflow run ID is going to be 1234. OK, great. The gRPC server will receive that request. And naturally, the first thing it does is it produces a record to Kafka. And that record we call affectionately in LittleHorse as a command. And the command has two important things here. Number one is the payload, which is what does it do, which in this case is run a workflow with the ID 1234 and probably a bunch of input variables and the workflow spec name and a bunch of other stuff like that. The other interesting thing is that it has a command ID, and this is how we provide synchronous responses, even though Kafka is technically an asynchronous system. So while that command is propagating through Kafka, the gRPC server is going to open up a request either in memory to the same LittleHorse in the same process, or over the network to another LittleHorse server instance, depending on whether it's horizontally scalable or not and where the partitioning falls, saying, hey, I care about the response from command ABC. Can you please send me the response back when you've processed it? And then at the same time, this command, which is this big blue box, is going through Kafka. It's just a record in Kafka. And it'll eventually arrive at the stream processor. The stream processor is going to think about it for a minute, and it's going to decide, OK, well, time to create a workflow run with the ID 1234. Also, this gRPC server politely asked, can you please tell me what happens when this command is done? And this is command ABCD. Someone's waiting for command ABCD. Let me return the result. So I'm going to send workflow run 1234 to that result, to that waiter, and then it will eventually end up back at the client. So in this way, we are able to kind of use Kafka as a distributed commit log. It's not an asynchronous processing system, but it is a distributed commit log here. And we have put a synchronous facade over Kafka. And you might be asking, well, doesn't this take forever? Actually, it really doesn't, because Kafka is quite performant. You can do it generally at 10, 15 milliseconds. So that is the way writes work in Kafka Streams, and sorry, in LittleHorse. And a couple key points to remember are because of the way Kafka Streams works, the only way to modify what's in RocksDB correctly is while processing an input record in the Kafka Streams topology. And there's a bunch of reasons for that. A lot of it goes around the fact that you need to use the Kafka Streams framework to publish updates to the changelog, and you also need to wrap those updates into a transaction, especially if you're using exactly one semantics. We've just covered most of what's on this slide, which is that all things that happen in a workflow, like run a workflow, or this task was completed, this task was started, this task is timed out, this user task was completed, all of those things are updates on a command topic, and they're partitioned by the workflow run ID. So all of the commands for a particular workflow end up on the same partition, which means on the same streams instance, same streams task in the same RocksDB instance as well. And that also allows for strong ordering, which means because every record in a certain partition is processed one at a time, that means that the processing logic for dealing with a certain workflow run can be, we can assume it's always single-threaded, which actually makes the code a lot easier than some other workflow engines. And one other thing I'd like to point out is that for the most common command that we observe inside LittleHorse, which is noting that a task run was completed, we end up actually having 7 reads and 8 writes, which are all interleaved, and they all kind of depend on each other. So there's a lot of round trips back and forth to the state. So let's take a look at the network diagram for how that looks in LittleHorse. There's the network diagram for those round trips in LittleHorse. And the reason for that is because RocksDB is local. Well, some other workflow engine uses Cassandra as a backend. I won't name them. And that's what their network diagram would look like. So this is one of the reasons why LittleHorse is able to have good performance, is that the network there's not a lot of network round trips going back and forth between LittleHorse and the state when we're processing a workflow. Now, it is true that writing to RocksDB results in a write to the changelog topic. That is true. However, remember that in Kafka, most writes are batched. In fact, if you've configured your producer properly, all writes should be batched. Whereas in this diagram on the right, you have to have multiple network round trips just for one command. Whereas in LittleHorse, you can have about 100 commands, which are all batched in the result of all the writes for one command are batched into one request to the changelog topic, which means there's less load on the brokers, which is kind of our data store. Which means the Kafka cluster we have to have will be smaller than the Cassandra cluster you would need for a similar load in a Cassandra-based workflow engine. What about metadata? And I bring this up not because we're going to talk about how it works in LittleHorse, but because one of my favorite features in Kafka Streams is global tables. The challenge here is there's a cluster of LittleHorse servers, and they all have their own input partitions and so on and so forth. But as a user of LittleHorse, the workflow, I define one workflow, which is the order processing workflow, and I want that workflow to be that workflow specification to be constant across all of my workflow instances. So that means every single LittleHorse server instance needs to know about that workflow specification. Kafka Streams has a great way of doing this, and that is called a global store, which is basically a way where you can have one global store and you can broadcast it in a read-only manner to all Streams instances. And this is great for a lot of things like any metadata use case. The limitations of this are that you should not put enough state in your global store that it cannot fit on one server. And it also, you should also make sure that it's very quick and easy to restore, which means generally you want to keep it under 1 GB, because if you have to restore any longer than that, it will block the processing of other tasks while a new Streams instance is starting. So now I want to get into another Kafka Streams feature, which you all may or may not know about, and actually was inspired by Flink. But that feature in Flink is no longer available, actually. Interactive queries in Kafka Streams. So in LittleHorse, we have to read the status of a workflow. So if I have some failure somewhere, I want to know, why did this workflow fail? I want to see the stack trace. I want to be able to also search for workflows. So I want to find, I have an angry customer. Obi-Wan's mad that his lightsaber order didn't go through. I want to find the workflow with email is obiwan@kenobi.com. I want to find all workflows that have failed. These are some searches that we have to do. Also certain time-based queries, like any failed workflows, yesterday. We don't have time to go through how we allow for secondary indexes using Kafka Streams, but the important thing is how do interactive queries work, and that's what most of you guys would do while building your own Kafka Streams applications. So we're just going to go with, I want to get the status of a certain workflow. I want to see what's going on in one workflow. So this is another diagram of how LittleHorse might work. We have the command topic, which is what does the bulk of the processing in LittleHorse. Here has 2 partitions, and we have 2 LittleHorse server instances. And you can see there's 3 workflow runs. There's 1, 2, 3, 4, 2, 3, 4, 5, and 3, 4, 5, 6. And there's a couple commands in the topic saying things are going on in these workflows, and these server instances are going along happily processing them. So let's say a client comes along and says, hey, I want to get workflow 1, 2, 3, 4, and that request just ends up on server 1. Well, server 1 would check a bunch of RocksDB instances and say, hey, well, here's the answer. I have workflow 1, 2, 3, 4. But what happens if the client says, hey, I want workflow 3, 4, 5, 6? Well, let's just say magically the request ends up arriving on server 1. In this case, what happens? We don't know, because server 1 doesn't actually have workflow 3, 4, 5, 6. But Kafka Streams actually has a solution for that, and it's pretty cool. If you recall, in LittleHorse, all data is partitioned by the workflow run ID. So the workflow run ID, in this case 3456, is the partition key. And Kafka Streams Interactive Queries has this method called query metadata for key, where you take in the name of a store and a partition key, and you provide a method that serializes the key. And what it will do is it will return metadata for the Streams application instance that hosts that the partition for that key. So in this case, it will give you the host info of server 2. And then basically it's incumbent on you, the application developer of Kafka Streams, to make a network request to that host. And then that host will return the information. So the second screenshot we have down here shows you how you can actually get a store in Kafka Streams interactive queries. And that basically gives you read-only access to what's in RocksDB. It's important that it's read-only, because if you write to RocksDB from outside the processor context, the thing processing input records, it's not necessarily wrapped in a transaction. Kafka Streams, the framework doesn't know about it, so it doesn't get distributed to this changelog topic. So it is only read-only, but it is a very, very useful thing that is actually at the core of LittleHorse. And if you're not using interactive queries in your Kafka Streams application, there's a lot of stuff you can do. So for example, if you have a Kafka Streams app that is computing some state and then you're using Kafka Connect to throw it into some other database and you're querying that other database, you might actually be able to save yourself the Kafka connector and the database just by using interactive queries. So I highly recommend checking it out. But in any case, back to the demo of how LittleHorse works. What happens here is when the client asks for workflow 3456, LittleHorse server instance 1 is going to go to Kafka Streams and say, hey, for this partition key 3456, what server is the host? And Kafka Streams will say, oh, go ask server 2. So server 1 asks server 2 for the result. Server 2 says, here's the result. And eventually it ends up back at the client, which is really, really cool. But what happens when something fails? Because the whole point of LittleHorse is that it's allowing you to build microservice applications that tolerate failure. That won't really work if the workflow engine itself fails. And if you're building Kafka Streams pipelines for mission critical things like fraud detection, you don't want your fraud detection pipeline to be down for a while. So I've hinted about changelog topics about 10 times without actually explaining what they are. When you do store.put key value in the processor API, or any other stateful application using the DSL, any other stateful operation using the DSL, what happens under the hood is Kafka Streams will first write into RocksDB the key and the value. And then the next thing it does is it writes a record to the Kafka topic, the changelog topic, with the key of the message, the key of the record being the key that you put into RocksDB, and the value just being the bytes that got written into RocksDB as well. So that will allow you, in the case of a failure, to recreate the state of what was in RocksDB just by replaying the changelog. And the way it works to provide exactly one semantics is a little bit complicated. Read KIP 892 if you are more interested in that. We won't have time to go into it today. But basically, the changelog topic provides durability for your Kafka Streams applications. And additionally, if you start out with 2 Kafka Streams instances and then Black Friday is coming up, you now need to scale out to 6. If there's a lot of state on your first 2 instances and you need to move them over, you need to add new instances. The new ones might be missing some context for, if you're doing word count, all of the words that have been processed in the past, so they can regain that state by reading through the changelog topic. So that's another thing that the changelog topic does. Unfortunately, reading the changelog topic can take a while, so we'll talk about how Kafka Streams open source mitigates that, and then I'll make a quick plug for responsive, which I have no relation to, and how they handle it. So let's say your Kafka Streams application or LittleHorse, either one, is just happily processing along, and suddenly something bad happens, and one of your instances goes offline. Well, all of the state that was going into task 2 in that RocksDB has been written to this changelog topic, right? So while this is, eventually there's this configuration called session timeout milliseconds, which is how often or how long a consumer can go between pulls or between heartbeats before the Kafka broker decides, hey, this consumer is dead, we need to do a rebalance. So after that session timeout, which is by default, I think 30 or 45 or 60 seconds passes, then Kafka Streams will say, oh, time to move this task over. So then this task comes, but it doesn't have the state, so it'll start reading from RocksDB, from the changelog and putting it into RocksDB. And it'll be reading from changelog and putting it into RocksDB. And eventually it'll be happy again and then start processing. Problem with that is that customers tend to be very grumpy when your workflows are stopped and you're waiting for the changelog to restore. So how does Kafka Streams allow you to get around that problem? And the answer is you don't necessarily need to wait for something bad to happen before you start taking precautions. And Kafka Streams standby replicas allow you to have really, really quick failover in the case of something going wrong. So in Kafka Streams, you can create a standby replica, which is basically a RocksDB instance and a thread that is restoring the state in real time, maybe about 100 milliseconds behind the actual active task, and giving you a hot standby replica, so in case something bad does happen, you already have the state for task 1 on your other Streams instance, and you're able to, as soon as the session timeout passes, have a quick rebalance, and then only have maybe 100 milliseconds or 1 or 2 seconds of state to catch up on, and you can resume processing once again. So basically, we've established that you can lose Kafka Streams instances and recover state. If you lose all of them, then you're going to have a very painful recovery. but it seems like your state in your Kafka Streams application or the state in your LittleHorse server is as durable as the backing changelog topics. So in LittleHorse, this means if your Kafka cluster isn't blown up, your data that's in LittleHorse is also not blown up. Kafka has very many primitives for making itself reliable. It's, in fact, a very reliable system. And I recommend this talk by Matthias J. Sachs, who's also, I call him the grumpy maintainer of Kafka Streams with all sorts of affection. He is the tech lead on the Kafka Streams project. And basically, the 30-second pitch is what you want to do is set replication factor to be 3, minimum in-sync replicas to 2 on all of your changelog topics and also your input topics, and you're pretty much fine unless something really, really, really bad happens to your Kafka cluster. So, you know, there's a lot of gymnastics involved in how LittleHorse works under the hood. And in fact, I've asked so many questions on the Kafka Streams channel that when I was walking the halls, people thought, oh, are you building a Kafka Streams company competing with Responsive? And the answer is no, I'm building a workflow company. But that just shows you how many questions there have been and how many times we've had to go debug the Kafka Streams source code and figure it out. But why did we actually do this? And the reason is the magic of batching. And I feel like I should mention the Kafka Streams community has unofficially adopted the otter as the logo for Kafka Streams. So you'll notice the first slides had the otter and the LittleHorse slides had the LittleHorse logo, but now we're talking about Kafka Streams and LittleHorse together, so we have a horse and an otter. But the magic of batching is that one single partition, which is the unit of scalability in a Kafka topic, in a Kafka Streams application, can process a massive amount of workflows. So you can process on one partition 1,050 task runs per second per partition, which is pretty crazy. And in fact, at the Kafka Streams level, that's 3,150 commands processed per second. And we've done extensive profiling on this. What is actually the biggest bottleneck is serialization and deserialization, but particularly deserialization of the records in your Kafka Streams application. So if you want to improve your performance, the biggest easy win you can do is moving from JSON into protobuf. When LittleHorse has been rewritten like 3 or 4 times before it turned in from a project into a company, and we got 5x performance improvement just by moving from JSON to protobuf. Highly recommend you do that. And the reason for that is, as I said before, all records are processed sequentially. So if it takes 10 milliseconds to process a single record, and 9 milliseconds of that is deserialization, in 1 second, you can process only 100 records. But if it only takes half a millisecond to process a single record, in 1 second that allows you to process 2,000 records. So the processing latency, which is a metric, process latency average, process latency max in Kafka Streams, is the biggest determinant of not actually latency of your application, but rather the throughput. Anyways, back to LittleHorse. Some older benchmarks from June 2023. Cluster was 6 servers, 48 cores total for LittleHorse, and I think it was a 3-node Kafka cluster, able to process 16,000 or 15,900 workflow tasks per second, which is pretty big. I don't want to talk about competitors and their benchmarks because this is talk about LittleHorse, but in any case, new benchmarks are coming soon, and all of those numbers are basically due to the Kafka Streams architecture. So some alternatives to Kafka Streams would be single leader SQL, like Postgres or MySQL or something like that, or Oracle, if you're 500 years old. And the problem with that is there's no real horizontal scalability, and the fault tolerance and failover story isn't as good. There's also distributed NoSQL like Cassandra, and you get better fault tolerance and you can have horizontal scalability, but it's still more expensive because of what I showed you earlier with the network round trips that you have to have. Also, distributed SQL, there's Yugabyte, which is a horizontally scalable Postgres. It's fantastic. If it weren't for Kafka Streams, LittleHorse would use Yugabyte. And Flink, you should know by now that it's not possible to build LittleHorse on Flink. And Kafka Streams and Flink are apples and oranges. You should not compare them, but I do prefer apples. And the other option is you could build this from scratch. And in fact, 2 of the LittleHorse competitors built streaming systems pretty much from scratch. But why do that when there is this amazingly performant open source solution that embeds RocksDB called Kafka Streams? And Camunda's architecture, actually, they have a broker, and they use RocksDB embedded inside of it to build something very similar to what we do, except they didn't quite, their replication protocol is not as performant as Kafka is. So I cannot take any credit for that, but I just, was lazy and decided to use a bunch of open source stuff. So the moral of the story is long live the otter. Kafka Streams is amazing, and if you're walking the halls, there's no Kafka Streams marketing, but Kafka Streams is great. This is a more in-depth diagram of the LittleHorse Kafka Streams topology built by KSTD, which is Hartmut Armbruster has released an Excalibur library for visualizing Kafka Streams topologies. It's pretty cool, the library and also the topology, but I think that pretty much wraps it up. A couple interesting talks that I find really, really good. I also highly recommend checking out Responsive, the fully managed Kafka Streams thing, which solves a lot of the state restoration problems. And they also have some of the best blogs on how to operate Kafka Streams applications. And also, please, check out LittleHorse on GitHub. Give us a star, read through our architecture, and thank you for the time.